Warning: aniline is toxic. Concentrated sulfuric acid and hydrochloric acid are corrosive. Wear gloves when handling them. Hi guys, here is MIH. Recently I've been exploring the history of the synthetic dye industry and stumbled across some of the earliest synthetic dyes. Interestingly, many of them can be made from easily accessible precursors in labs. In fact, there are three early dyes or pigments, namely aniline black, mauveine, and aniline yellow, that can be made from the same chemical, aniline, which you can tell easily from their names. So today I'll try to recreate the first dyes humanity ever made. To make the dyes, I'll need some aniline. Aniline isn't exactly a commonly encountered chemical, so it isn't easily available, but there are many ways of making it, such as the reduction of nitrobenzene demonstrated by NARED and many others. But there is an easier way of making aniline that doesn't need to deal with toxic benzene or nitrobenzene: the decarboxylation of p-aminobenzoic acid, which is commonly sold as a supplement, although I just bought it from a chemical company. To start, I added the whole bottle or 100 grams of p-aminobenzoic acid into a flask. My crystals were slightly yellow due to oxidation, but the pure chemical should be white. The flask is then heated with an electric stove, and the acid at the bottom quickly melted. After a while, everything melted into a dark liquid, and some colorless distillates started coming over, which I collected in an amber glass bottle. I transferred a small amount of the distillate into a conical flask and added some water, and you can see that the liquid is heavier than water and refracts light a lot, both of which indicates that we have aniline. The colorful droplet of aniline is really beautiful and interesting to watch. Soon, nothing more distilled over, and a chunk of brown stuff is left in the flask, which can be washed out easily with water after breaking it up. I poured the aniline over some sodium hydroxide to dry and stored it in a bottle. I didn't bother to redistill it, as the aniline produced this way should be pure enough for my use. Now we have our aniline, we can start making dyes. My original plan was doing a total synthesis of methyl orange via a couple of steps, but I screwed up in the first step as I tried to make sulfonylic acid, but instead made a bunch of tar. Oh well. I then tried to make a chemical called mauveine, which was the earliest synthetic dye. It was accidentally made by the British chemist William Birkin in 1856 during his quest of synthesizing the famous anti-malarial drug quinine. He tried to oxidize N-alloaniline with potassium dichromate in the presence of sulfuric acid, and although he didn't isolate quinine, he observed a rich purple color when cleaning the reaction flask. This exact purple later started a long-lasting trend in fashion and clothing, and eventually led to the birth of the synthetic dye industry. Anyways, to start making mauveine, I added 0.4 milliliters of 90% sulfuric acid into 200 ml of water. I then added 0.33 grams of aniline, which first sank to the bottom and then quickly dissolved. Next, 0.3 grams of potassium dichromate was added, which dissolved to give a distinctive yellow color. The mixture was then heated to 75°C for 4 hours. Even before the right temperature was reached, the mixture darkens as the reaction starts. What is happening is that potassium dichromate oxidizes aniline in an acidic medium in a series of reactions to form pseudomauveine. The chemical is called pseudomauveine because mauveines are actually a class of chemicals with the same core structure, but with different number and positions of methyl groups on the aromatic ring. Other mauveines, like mauveine A or mauveine B, are each made using a mixture of aniline, p-toluidine, and O-toluidine in different proportions. I don't have access to toluidines though, so I just opted to make pseudomauveine instead. Just as a side note, although the derivatives of mauveine are often used as mixtures, they have slightly different colors. The ones with more methyl groups have reddish colors, while the ones with less methyl groups have blue tones. But as you'll see later, my experiment results didn't exactly align with this conclusion. After 4 hours of heating, the now brown mixture was taken off heat and filtered. A small amount of brown-black residue was collected in the funnel. As mauveine is insoluble in water but soluble in ethanol, I added some ethanol to the funnel and filtered it again. This time, a beautiful crimson filtrate leached out, which is our mauveine dissolved in ethanol. Although the color of it didn't align with the literature, I was still very happy to see that at least something with color has been made successfully. Although mauveine was a great dye, it has a rather complicated structure and variable composition, which poses difficulty for chemists to find other dyes and pigments based on it. Fortunately, 5 years later in 1861, a new compound called aniline yellow was discovered, which was the first member of the azo dye family. The family quickly grew to account for 70% of all synthetic dyes produced in the world today. So what are azo dyes and why are they so important? Azo compounds are compounds that contain an azo group, or in other words, two nitrogens that link two other organic groups together. If the organic groups are aromatic, the resulting molecule often displays a vibrant color due to conjugation effects between the aromatic rings enhanced by the nitrogen bridge. Because there are a lot of organic substituents that contain an aromatic ring, countless types of azo dyes that each have slightly different colors can be synthesized. The compound we will be making today, aniline yellow, is one of the simplest azo dyes with a phenol on one side of the nitrogens and an amino phenol on the other side. Another reason why azo dyes are so popular is that they are readily synthesized by the coupling reaction of a diazonium salt and an electron-rich arene, which is exactly what I will do now. To make aniline yellow, 4.5 grams of aniline was measured out first, and 30 ml of 12% hydrochloric acid was added to it. The hydrochloric acid immediately reacts with the aniline to form a water-soluble salt. 4 grams of sodium nitrite was then measured out and dissolved in 20 ml of water. The aniline solution was placed on an ice bath to cool, and the sodium nitrite solution was slowly added into it. This reaction is known as a diazotization reaction, where an aromatic amine reacts with nitrites under an acidic condition to give an arodiazonium salt, in this case, phenoldiazonium. Diazonium salts are useful in organic synthesis as they are very reactive and can combine with many other nucleophiles, for example another aromatic ring, to form a bond between the carbon and the nitrogen and thus form our azo dye product. Consistent with this reactivity, diazonium salts are also unstable at high temperatures, which is why an ice bath is used. As more nitrate was added, the aniline solution produces traces of yellow color but quickly disappears after stirring. The yellow is actually our aniline yellow product, but it is not supposed to appear here and should appear later. Now let me explain things a little bit here. The azo coupling reaction requires a diazonium salt and an electron-rich arene, but as you've just seen, diazonium salts can be made from aromatic amines easily, while an aromatic amine is electron-rich in nature. Therefore, as our diazonium salt forms, it could react with the remaining aniline in the solution and forms our dye prematurely. This unwanted reaction could be limited by strong stirring and temperature control, but I did neither of them, so I just have to account for the loss of yield. I'm actually not really sure why the dye redissolves though, as the azo coupling reaction should not be a reversible reaction. But even if a little bit of dye forms here, it's fine, because in the next step we'll convert all of the diazonium salt into the dye by adding in more aniline. For this, 4 grams of aniline was measured out and dissolved in 8 ml of 18% hydrochloric acid, and the resulting solution was slowly added into the diazonium salt. As more aniline is introduced, the orange color of the diazonium salt gradually lightens into the yellow color of our product, aniline yellow. However, after adding everything in, the mixture somehow turned orange again, so I quickly made some more of the aniline solution and dumped it in, which quickly turned the orange into a yellow. The mixture was then filtered, and the residue which contained our product is dissolved in ethanol, yielding a surprisingly dark red solution. Aniline yellow has several interesting properties. For example, its ethanol solution is dark red, but adding water in it results in the precipitation of the bright yellow dye. It is also a pH indicator and turns red when hydrochloric acid was added, but turns yellow when potassium hydroxide was added. This is actually not surprising. Many azo dyes are acid-base indicators, including the most famous methyl orange I originally planned to make. However, azo dyes usually display warm colors such as yellow or red in both acids and bases, so it could be hard to distinguish the color at the color transition point, which is why other dyes like phenolphthalein, which have sharper color changes, are used. The last thing I decided to do was adding 1 drop of the dye's ethanol solution into a vial of water, and the yellow color was really beautiful. Now for the third and final dye. I said in the beginning that I wanted to make aniline black, but it just has a black color which isn't very interesting. However, upon research, I found a related compound called emeraldine that not only has a beautiful green color, but also is electrically conductive. Both of these properties really surprised me, so I decided to make it, despite it not exactly being one of the earliest dyes. To start, I measure out 2.05 grams of aniline and mix it with 38 ml of 1 mole hydrochloric acid in an ice bath, but I found later that the ice bath wasn't necessary. Then, 2.28 grams of 7.5% hydrogen peroxide was measured out and mixed with 20 ml of 1 mole of hydrochloric acid. The peroxide was slowly added to the aniline solution under stirring, and the mixture was allowed to stir for 3 hours in room temperature. In this reaction, hydrogen peroxide oxidizes aniline in an acidic medium via a radical process to produce a variety of polyanilines, which are basically chains of aniline molecules connected together. Interestingly enough, different oxidants gave significantly different products when they are combined with aniline, probably because of the different mechanisms. The dichromate gave mauveine, which we just saw, while hydrogen peroxide and ammonium persulfate gave polyanilines. Depending on the extent of oxidation, the polyanilines have different properties such as their color and their electrical conductivity, and are thus given different names. Here we are making the salt form of emeraldine, which is the moderately oxidized form with half the nitrogen atoms protonated. If we add less peroxide, we would make the pale yellow leucoemeraldine, while more peroxide would lead to the formation of the violet-pernigranine. The reaction mixture slowly changed color to a very pale shade of green, indicating that the reaction worked and we're indeed producing some emeraldine. 30 minutes later, the blue-green color was much darker, and some precipitates formed, which is our product. I vacuum filtered the solution, and we have some nice emeraldine collected in the funnel, while the filtrate was a pale yellow color, possibly due to the presence of the partially oxidized leucoemeraldine. Very interestingly, emeraldine can also be produced by an electrochemical process, so I tried electrolyzing a dilute solution of aniline and hydrochloric acid with a graphite and titanium electrode, and to my surprise, a very pretty blue color was produced. If we look closer, the graphite anode is letting off some dark colored matter, which is some form of polyaniline. Obviously, what I'm doing here is very crude and inaccurate, but industrial processes use similar setups to coat a layer of conductive emeraldine onto a substrate, which find use in sensors, capacitors, batteries, and many more applications. So there we have it, 3 of the world's first synthetic dyes recreated in a lab. I was actually able to make a rainbow-like array of them by dissolving the dyes in ethanol or water and fine-tuning their concentration. As you can see, synthetic dyes are very interesting in their structure, synthesis, applications, and many more. I hope you learned something here today, and see you soon.